Thank you for inviting me here, Randy, to share a little knowledge and experience with that we've been through with understanding failure conditions of high voltage bushings on both transformers and breakers, and to answer your question about what is OIP and RIP. We'll go back even before that and look at the different types of construction of that are found today on utility systems around the world. One of the earlier styles, aside from wooden bushings from way back when, is one with what was called resin bonded paper, RBP type bushings that were fabricated long before the 40s and into the 30s at that time. These were, again, it's a paper insulated, but with a resin bonded paper. And the problem with these, they worked at the time, but over time, they've shown a propensity to suffer from high dissipation factors and partial discharge. Typically, you'll never find these on the systems today. So we're not going to talk about them today. OIP stands for oil impregnated paper, and this refers to the insulation system inside the bushings that makes up the condenser. They've, excuse me, first came out in the 1940s. It's the predominant bushing that's in use today. People understand the technology, and they can sustain a lot of, I use the term abuse, but use, and they have proven over time to be much more reliable than RBP bushings. In the 1990s, we began to see the introduction of what we call resin impregnated paper, or dry type high voltage bushings. These were considered to be a safer alternative to OIP by virtue that there is no oil inside the RIP type bushing. It's a dry insulation system. So that if and when these things fail, you can reduce the risk. Well, there is no risk of explosion and shrapnel going from the porcelain on the high voltage bushings when they have failed catastrophically. So it's more and more now people are moving in this direction. The good news is when they fail, they kind of like don't explode, but the point is, nonetheless, they still do fail. And then so this is with these types of bushings, it's excuse me, more or less maintenance free. They're not porcelain, shell on the outside. It's a resin. It can sustain temperatures up to 120 degrees C, and it has a much better seismic withstand capability than porcelain, than bushings. So in some cases, they're considered more reliable than OIP bushings. That comes at a cost, and there's different operating characteristics associated with these types of bushings that need to be taken care of. So Cigre, which is a worldwide body of experts around the dealing with equipment of above 1,000 volts around the world, we went through what we call the Bushing Reliability Survey. It was published in February 2019. And basically, the members of the working group contributed their data on bushing failures. And it was found that transformers before 1980, the bushings were a cause of 15.9% of all transformer failures. The other side of the coin here is that when bushings do fail unexpectedly and catastrophically, the coincidence of a fire is like 30%. It does take the transformer with it when these bushings fail unexpectedly. So when we look at the failures of transformers, a higher propensity of failure of the transformer is due to one of the bushings on the transformer. And so when you look at the data from that study, we look at the transformer failures caused by bushings in different parts of the world and different times, that there's quite a higher number of transformer failures where the root cause was failure of the bushing. So what makes a bushing fail? Well, it's the insulation system inside the bushing, which is totally sealed away from the rest of the transformer itself. The oil in the bushing should not be mixing with the oil in the main tank. So it's a condenser inside, basically a condenser inside the bushing, where foil and paper is wrapped around the conductor as the lead passes through it. So what happens is, and we heard before about moisture ingress is one of the prime causes of insulation failure. And this is understood because paper leaks through gaskets at the top of the bushing is one of the favorite spots where things begin to come into it. We all know that oil and water don't like to mix. So as moisture enters the bushing, it goes into the oil. Oil doesn't want it, but it passes easily into the paper insulation around the bushing. As that becomes more and more wet, the dissipation factor increases, and the result of resistive currents result in increase in temperatures causing breakdown. That's more or less the process. There's also, with moisture inside, the evidence and opportunity for partial discharge to begin inside the bushing insulation system itself. And it's difficult to detect because the PD inside a bushing or inside a transformer is very periodic bursts of larger activity. And the amount of the activity is related to typically the location and also the amount of material involved in that particular area. The danger side of this is that these PD activity does produce gas. It does eat away at the layers of insulation inside the bushing itself. And as discharge increases, energy increases. There are small holes will eventually form what will continue to increase in size. And it begins to short out the layers of the condenser coil itself, condenser inside the bushing itself. Excuse me. Now that's OIP type. RIP type, typically because it's a solid insulated bushing, there is no oil inside it. So the insulation system is completely different. The weather sheds on the outside are hydrophobic, so they repel water. Whereas if it's porcelain and becomes contaminated, it has the propensity to keep water on the surface of the porcelain itself. So therefore, resin bonded paper and actually epoxy resin bonded paper used in RIP is more resistant to moisture. But the insulation system degrades over time. Usually in a very small area, it can start with a void. There can be partial discharge develop inside, again, from following the manufacturing process if there's minute voids left in the construction of the bushing itself. Part of that Cigre study, and if you are a Cigre member, you know how to get a copy of this. It's free to Cigre members. However, if the guide itself is more than 3 years old, you're able to go into the Cigre website and obtain this brochure for free. All they want is your contact information. But this is a failure mode of an RIP bushing. And here you can see the layers, the concentric foils that have wrapped around. This is one where discharge started. And it basically it grew between the capacitive grading layers. So it just begins to short out the capacitive layers inside the bushing and create this discharge energy increases. The small holes will eventually form and they'll continue to increase in size. That is what the failure of an RIP bushing looks like. So the anatomy of this is there is a way to detect these failure conditions, and it's through, so long as the bushing has the test tap or the C1 test tap available, we're able to utilize that and install a sensor onto all 3 phases of the bushing. And from that, we measure the C1 leakage current of the bushing in operation. The current, the lead is then brought down into a monitor where we do measurements and a bunch of calculations on it to derive when things are normal and when things are, more importantly, when things become abnormal. So on the excuse me, on the right hand side, you can see the bushing with with the sensor installed on the tap, and it all starts with the sensor and a proper installation done. So on the left hand side, you see this is with the bushing sensor installed and with flexible metallic conduit for protection of the coax cable running from the sensor down down below to the monitoring system. We did have one case here where improper installation of the bushing sensor began to generate false alarms, and it was due to moisture ingress resulting from the improper installation of the gasket between the bushing sensor and the flange of the bushing tap. And what you see here is in blue the total imbalance current as going up and down with as the thing was breathing moisture. The leakage current, or the phase angle in this case, because we're measuring two things, we're measuring leakage current and phase angle. And once there was a whole bunch of false alarms. Once we saw the data, we suggested to the customer that you go back, or we went back and corrected the situation and instructed them how to go about doing a proper job of installing it. And after that, things were fine, as you can see on the right-hand side. So a lot of discussion previously about gaskets. Well, they're a really important job when we're looking at the transformer. So the principle of the operation looks like this. We have 3 bushings, and each with their own tap sensor. The sensor signals come down into the monitor, into what we call a balancing unit, because each bushing is going to be, when it's energized, it's going to be having a different amount of leakage current coming out of it. We do a balancing and summation of the vector sum of the currents into it and the summation unit, and there's the equation that you see above it. And from there, so we can arrive at a null point inside the monitor. And it's from that null point that we monitor both the increasing potential for increasing leakage current and or phase angle of the measurement of each bushing in sequence. So what's the effect of dissipation factor, power factor on the bushing currents? And this is of a 345 kV bushing. Excuse me. So what we're seeing here on the scale on the left-hand side is the leakage current being measured. And yes, so what we're seeing here is as the phase angle changes, you can see the C1 number changes as well. So the phase angle, this is indicative of a dissipation factor problem inside the bushing. As the phase angle continues to change, or change, the leakage current is increasing over time. So this is how we determine how dissipation factor change from a capacitance change in the bushing current itself. So over time, as the power factor changes, the leakage current IPF changes over time as well. And we know that dissipation factor is very sensitive to moisture and to voltage, to the point that we conducted an experiment quite some time ago on this defective 69 kV bushing. And what you see here is a plot of different conditions of testing the bushing. So in the blue plot across the bottom, line trace number 1 shows the typical 10 kV at 25 degrees C corrected power factor test value, as you would do manually on a bushing on a transformer. And it shows good results, I would say, tested at 10 kV and 25 degrees C. Trace number 2, the one in pink, shows it again 10 kV measurement, but now the oil temperature is at 70 degrees C. The bushing temperature, I should say, 70 degrees C. And you can see now that the dissipation factor has increased ever so slightly, and is indicative of a failing condition of a bushing. When we also took away the trace number 3, we tested the bushing at 70 kV at 25 degrees C. So in other words, at full potential rather than 10 kV. And you can see here that the dissipation factor is jumping all over the place. And then at the trace number 4 shows at 70 kV and 70 degrees C bushing temperature that the dissipation factor is all over the map. So this is the function. Excuse me. So this is why in doing offline testing, sometimes doesn't always reveal problems of bushings that are in fact having problems when they're energized at full potential and operating temperatures. This is a key important thing to understand. So now we look at the capacitance component of the leakage current. Again, 345 kV. And here we're looking at magnitude. So here the phase angle is not changing. Whoops. But the phase angle is increasing. Therefore, the leakage current is increasing. Therefore, the capacitance is increasing. So foils are being short-circuited inside that bushing in this case, where you see the changes in capacitance are reflective of the leakage current change. Now, to understand this, when looking at the monitor, this is what one could see as a result of alarms coming from a bushing monitor. And if given the software provided by the vendor, you're able to see this data in terms of a polar plot and also trending. In this case, it's showing each blue dot you see in that polar plot is representative of a measurement made over time. And so there's a whole bunch of measurements being made here, but it's pointing in this case at a capacitance change, significant capacitance change in the bushing. This is a software that's helped use to understand this capacitance change and which phase is having the issue. When you look at trending of the same data that you just saw in that polar plot, and you look at this, here we see the up the left-hand side of the scale for the summation of the leakage current and over time. And we're seeing changes in the leakage current over time. And the big question is, well, why is this happening? And it turns out that there's a relationship between the top oil temperature of the transformer, which of course is surrounding the base of the bushing, and leakage current. If there is a defect beginning to happen inside the bushing insulation. So we call this as a temperature imbalance current. And every time that the temperature, in this case, you see the green goes above, in this case, I don't have the scale, but every time the temperature did increase, the leakage current as well increased. When it went back down, then the leakage current went back down. The same data, but now correlated to top oil temperature of the transformer. And we're looking at here in pink is the top oil temperature. So in this case, every time the top oil temperature was going greater than 40 degrees C, the leakage current was increasing. And then as the transformer cooled down from a loading point of view or a day point of view, we see the leakage current decreasing. So it's the indication of an incipient failure condition beginning to happen inside the bushing. And as always, the first clue that something is going wrong inside. And the monitor will alarm and present you with the data. Here's what's happening inside your bushing. So in this case, this bushing was, we call, saved from the point of view of early warning of a bushing in failure condition. And here's the case of correlation between the bushing current, phase angle, and temperature as well. So it all points to, in this case, a dissipation factor problem inside the bushing, which cannot be fixed, of course. In service, it has to be replaced. The point is, you have the warning that something's going wrong, take the outage, test it, repair it, replace it, I should say, and put it back in service. That particular bushing also revealed we had inputs for partial discharge signals. That bushing, the phase B, channel 2 was showing partial discharge inside the bushing as well. So that was contributing to the failure condition, and one more reason for them to hurry up and get it replaced. So when we're looking at saving bushings, the trend of the imbalance current is all important. It does change over time. It can change because of temperature change if it's defective, or voltage change, a slight voltage change on the bushings of the transformer, applied voltage on the transformer. But the point is, once it begins to increase, there's no going back. It has to be replaced. So in this case, we're looking at a correlation between the imbalance current and the bushing current on phase 3 of that transformer. So it overlays nicely. It's telling you which bushing is having the problem, so you don't have to go out and begin hunting for it. It was interesting looking at the data on the failures of trying to fix leaks on transformers. Here's a case we had with one of our customers. This one was on a 138 kV distribution substation transformer, and a bushing monitor had been installed on this for 2 years prior to this event coming up, and the alarm went, and they're curious readings that the owner came to us and said, "What do you think?" We said, and our experts looked at it and says, "Well, we think you have a leaky bushing, that the oil has leaked out of the bushing." And so they sent out an engineer to go and check it out. And here you can see when he got on site, there was no oil to be seen in the reservoir at the top of the bushing. And there was this large stain of oil flowing, leaking down the side of the tank as the evidence. And once the outage was taken, and when the outage was taken before, and go and check and see somebody had tried to do something about stopping the leak on the bushing, but that didn't work out very well. So in this case, it was no choice. They replaced the bushing, excuse me, and put it back in service. But looking at the data, you can see here that things with bushings, and we found this, is that things changes in bushing condition can happen over a relatively short period of time. In this case, we're looking at the light blue trace, which is the total imbalance current of all 3 bushings, and you can see it's where it should be. It's fairly stable, but on the 24th, it begins to increase, and increase quite a bit. And the green trace is the calculated capacitance in picofarad of the capacitance of the bushing. So we can see here, as imbalance current is increasing on this phase, the capacitance value is decreasing on the bushing. The yellow line and the red line are the alarm limits for in other words, the first alarm, and the red line is for the second alarm, meaning get your butt out there quickly before this thing shatters. So it was an interesting case that we saw this to detect a leak in the bushing and this is how the data shows. But you can see that it happened over a relatively short period of time, where periodic offline testing of a bushing or even inspection of a transformer may not have been enough to capture this failing condition on that bushing. So bad bushing failure of a transformer was averted. That's OIP bushings. With RIP, we didn't expect to see, I don't know why we expected to see the same sort of failure condition, but we were all surprised by when we captured a bushing failure of an RIP bushing in service. Here is the trend of data. This monitor was installed back in 2016, and after 50 days in service, the imbalance current measured by the monitor increased from just over 1 milliamp to 63 milliamps in an hour. This reflected an 85% change in capacitance in less than 1 hour. Now, when you read the IEEE guidelines for limits in terms of capacitance change on bushings as to action to take, it's interesting to see that if the capacitance change, this is with offline testing, if the capacitance change is greater than 5% from nameplate, it's time to replace the bushing. Here we have a rate of change, the change in capacitance of 85% in less than 1 hour. So, and there you can see every little blue dot there is a test, and there you can see once the monitor sees this fast increase, it's capturing data every 5 minutes or so and able to trend it. So we were surprised, the owner of the transformer was surprised, and the bushing manufacturer was surprised about how quickly things can go south with RIP bushing failures. This is the characteristic pattern. So this change in imbalance current was caused by the sudden change in leakage current of this phase C. So it again identifies which phase is having the issue. There is another failure mode of RIP bushings, and it came to light. I was at an IEEE Transformers Committee meeting when one of the experts from one of the bushing manufacturers gave us a small tutorial on application. Excuse me, of RIP bushings, application of RIP bushings. And I still remember his words. He says, you got to understand one thing. He says, the rating plate on the bushing of an RIP bushing, if it says 800 amps max, that means 800 amps, not 801 or 802. It's 800 amps. That's it. That's all. There's no capacity for overloading RIP bushings. Unlike with OIP bushings, there's some tolerance level, I would say, for overloading. And here's what can happen. In this case, now there's some conjecture about what happened here. Excuse me. But in this case, the top terminal of this bushing overheated. Some people say it was dissimilar metals. Some people said it was, oh my God, a bad connection, or no, you just overloaded the transformer. That's where the lawyers got involved. But you can see here, this did overload, and it cracked at the top. And that brown goop you see is the resin melting inside at the top and coming out. Now, so this bushing failed. The good news is that it did not blow apart, so to speak. It failed quietly, but it failed nonetheless. So this is one thing to be cautious about RIP bushings. Be cautious of the rating plate, and that if whatever it says, don't go beyond that. And also, like any other electrical connection, make sure you make a good electrical connection on it to avoid overheating of components. So from a conclusion point of view, we have OIP bushings that are affected by both changes in power factor and capacitance. We know from this changes in the dissipation factor are temperature dependent. They're also voltage dependent. Therefore, the effect of voltage and temperature on power factor depends on the contaminants that are present and where the contaminants are located in the bushing. Monitoring for this temperature dependency, as you saw, can be more reliable than trying to temperature correct the measurements. Don't try to do that. Just follow the performance of the bushing in service is going to give you a lot more information about the health and condition of that bushing. The other thing is when you remove the stress from the bushing, in other words, you take away the applied voltage and temperature, the leakage current and phase angle will change. Hence, you may not be able to verify the problem with offline testing, power factor and capacitance testing. That has happened in the past. One of the tests of last resort, as I call it, of testing an understanding condition of the bushing is to do a DGA test on the oil of the bushing. That, in my experience, has seen some real eyebrow-raising values of combustible gases in what was questionable bushings. And I'm talking about tens of thousands of parts per million of hydrogen in the oil of bushings, which was just waiting to explode. So, but that's, again, DGA is the test of last resort when all else have you scratching your head. And OIP bushings would generally do not fail in a linear fashion. In other words, the power factor and capacitance values rise and fall over time, but will grab this gradual upward trend over time. Changes in this power factor and capacitance can generate gassing, increasing the internal pressure and resulting in a violent failure. Whereas RIP type bushings do not typically exhibit changes in power factor because there is no oil, there is no chance for moisture to begin to impact the insulation system whatsoever. So the thing we're looking for in RIP type bushings is large changes in capacitance. And these, as you can see the data there, can occur quickly over the space of 1 to 2 hours. So when you receive an alarm from the monitor, review the data immediately. In some cases, the bushing will continue to operate with splits in the outer weather shed and with very high values of capacitance. And failures are typically less violent, but can still result in transformer failures. The idea of that bushing failure that we caught the first time, the utility that owned that transformer has a mix of OIP and RIP bushings in their fleet. They had a procedure when bushing alarms came in as to what to do. And this is important. The alarm response procedure for transformers is really, really something that people often forget about. That utility process was the alarm came in, they had subject matter experts look at, look at the data, determine, right, we need an outage, phone their friends in operations and say, depending on the trend, the rate of change of the data, arrange for an outage the following day. So now they can plan to get the right crew, the right equipment, the right bushing up for replacement and all that stuff prepared to take the outage, to test the bushing and confirm that it is bad and replace the bushing. When it comes to RIP bushings now and how extreme it is when they've changed when the failure rate happens, is now the principle has changed, the practice has changed, the response has changed to the point that now when that alarm comes in and it is an RIP bushing and they see that rate of change like that, the call is made immediately to operations to take that transformer out of service. Now, then go and double check and follow up the day after or when convenient to go and confirm and then go up for the bushing replacement. So it has resulted in a change in practice now, depending on the type of construction of the bushing. Is it OIP or RIP bushing? The changes, it made necessary changes to the alarm response to alarms from bushing monitors. So Randy, so here are the references, and I suggest that for those of us, for those of you who are Cigre members, you're aware of the value of these reliability surveys. One for bushings, TB 642. Sorry, that's the transformer reliability survey, which is really another interesting piece of work that should be looked at. And the bushing reliability survey, there's tons of pictures inside of how bushings fail and inside and things to be aware of on them. And it's, yeah, Cigre reference documents are a great tool for learning and educating and sharing knowledge with younger engineers coming into our field of expertise and sharing knowledge. So Randy, that's where we are. I'll take questions, Randy.
Thanks very much, Brian. Here is the first question. IEEE doesn't recommend C2 power factor limits for bushings, and neither a lot of manufacturers except ABB mention it in the nameplate. How can the owner monitor the C2P factor, power factor, if the benchmark C2PF reading is not available?
Okay, the short answer is you can't. It's and I don't know enough about why that is within the IEEE standards. Because C2 is grounded, to the tank of the transformer. That's one reason why it is grounded. So I can't explain why the rationale is behind that's why the IEEE or IEC in this case do not put any more emphasis on that. I just don't have an answer for that question. All I know is you cannot monitor it in real time. We only look at the active measurement, which is the C1 measurement leakage current.
Okay. Next question. How accurate and reliable is the frequency sweep test for C1 and C2 power factor? Should one replace the bushings if C1 and C2 readings are out of threshold limits at frequencies other than 60 hertz?
The answer to that is the sweep frequency response analysis. This is an offline test now, for those that don't know. It is far more sensitive and gives a lot more detailed information about the moisture condition in not only inside the bushing, but also inside the transformer when you do the test. And understand that the results of that often come up with the what I call the total available total moisture inside the solid insulation system of the bushing and or transformer. So it is a far more sensitive test, but it is an offline test, and more people are doing it. And it's also shown that things may look perfectly reasonable at the fundamental frequency of 60 hertz or 50 hertz, depending where you are, but the insulation system could be deemed wet when you look at the rest of the data coming out of that sweep frequency testing. These are the things that I have seen in it, where the frequency, standard frequency testing shows you everything looks okay, like that diagram I showed you before. But when doing it at multiple frequencies, it can reveal a whole bunch of other issues. So it's a far more sensitive test, and just don't go by the fundamental frequency test when you're doing it.
Okay. Next question. Is there a certain level for percentage power factor which could be considered as an alert, or the most important is the trend of change over time?
There's two aspects. Excuse me, Randy. When you were looking at, I always look at trend over time, and whether it's DGA or bushing dissipation factor from bushings or whatever it is, it's always trend over time. And you may be exceeding limits occasionally in trend over time, but if it's consistently beginning to trend over limits, recommended limits, whatever it is, over time, that's the time to be concerned and take action to find out why it's happening. So it's two things. One is over limits. The other thing, but more importantly, is trending over time. And you saw in some of the charts I was showing that sometimes the trending is slow evolving. Sometimes the trend is a function of another parameter, like top oil temperature of the transformer in the case of bushings. And in the case of RIP bushings, trending over time when it takes off like a rocket is the indicator, like don't hang about, don't wait to see if it's going to go up another 10% or 5% in the next 5 minutes. Take action now. It's telling you things are, the transformers, in that case, that bushing was in distress. So trend, it's all about trending.
Okay. Next question. If there is a rapid change of cap in RIP, how much time still available to take TX out of operation? Does it have a relation to the percentage of change of cap?
Well, as I said, in the IEEE world, any change in capacitance from the nameplate of the bushing itself, a change of capacitance from the nameplate of 5%, it's time to replace the bushing. So in that case, you saw on the display there, that change in 5% happened within the first, I didn't look at that closely at it, but within the first few minutes of the alarm coming. So it's telling you then, you have a bad bushing. You need to take action, and the action should be take this transformer out of service and go and verify. but so you're avoiding potential problems because RIP bushing do fail. They fail silently, they don't explode, but the point is they have been known to cause transformer failures as well. So don't hang about when you see that rapid rate of change in capacitance on a RIP bushing, as you saw. Take action, err on the side of caution, and get it removed from service. Don't hang about waiting to see how quickly it's going up, and you're not going to be trying to set any sort of record here, so to speak.
Okay, and thanks very much.
Thank you, Randy. Thank you all for sharing.